Hi everyone, this is Mrs. Pettit, and I'm here to talk to you today about inscribed and circumscribed polygons. If we start with our new definitions, a polygon is inscribed in a circle if all of its vertices lie on the circle. So let's try and draw a couple of examples. Let's try and draw a triangle inscribed in a circle. So let's start with the circle. And if we inscribe a triangle inside of that circle, all of the vertices will lie on the circle. If I want to draw a quadrilateral inscribed in a circle, again, I'll start with the circle, quadrilateral having 4 sides, so all 4 vertices will lie on the circle if the quadrilateral is inscribed in the circle. If a polygon is circumscribed about a circle, then each of the sides is tangent to the circle. So if I want to draw an example of a quadrilateral circumscribed about a circle, again, I'm going to start with the circle and do my best to make each of the sides tangent, meaning touching the circle in exactly one point, and the quadrilateral being circumscribed about the circle. Another way of saying that a polygon is inscribed in a circle is to say that the circle is circumscribed about the polygon. And if that's the case, then the center of the circle is the circumcenter of the polygon. So if we go up to our first 2 examples where we inscribed the triangle and the quadrilateral inside of the circle, the circumcenter of the polygon is the center of that circle. And likewise, if a polygon is circumscribed about a circle, we can say that the circle is inscribed in the polygon. And if that is the case, then the center of the circle inscribed in the polygon is called the incenter of the polygon. So let's try an example that will lead us to our first theorem of the day. If I have the diagram below, and I want to find the measure of angle A. If the quadrilateral is inscribed within the circle, then all of the vertices lie on the circle. So if I want to find the measure of angle A, the vertex is on the circle, and if I follow the sides out to the arc that is intercepted, the intercepted arc is 75 plus 30, which is 105. And if the angle vertex is on the circle, then the measure of the angle is half the measure of the arc. So the measure of angle A will be 52.5 degrees. To find the measure of angle B, again, identify the vertex, which is on the circle, follow the sides out to the intercepted arc. In this case, the intercepted arc is a 105 plus 75, which is 180. So the measure of angle B is the measure of its intercepted arc divided by 2. So the measure of angle B is 90 degrees. To find the measure of angle C, identify the vertex, which is again on the circle. Follow the sides out to the intercepted arc. This time, that's 150 plus 105, which is 255. So the measure of angle C is half of 255, which is 127.5 degrees. And to find the measure of angle D, find the vertex which is on the circle, follow the sides out to the intercepted arc, which this time is 150 plus 30, which is 180 degrees, and the measure of the angle is half the intercepted arc, and half of 180 is 90 degrees. So two questions that we want to ask now is, what do you notice about angle A and angle C, and what do you notice about angle B and angle D? It's probably quicker to notice something about angle B and angle D. Being that they're both 90 degrees, you probably notice that they are supplementary. And if you notice that, then go back and look at the measure of angle A and the measure of angle C, and if you put those together, 127.5 and 52.5 also equal 180 degrees, which means they are also sup. Which leads us to our first theorem that says if a quadrilateral is inscribed in a circle, its opposite angles are supplementary. Now let's think about what happens when we inscribe a parallelogram in a circle. If we go back and think about what it means to be a parallelogram, we know that opposite angles are congruent. And what we just learned, if a quadrilateral is inscribed in a circle, then opposite angles are sup. So if a parallelogram is inscribed in a circle, the opposite angles are both congruent and supplementary. And if that's the case, it leads us to our second theorem that says if a parallelogram is inscribed in a circle, it must be a rectangle. So if quadrilateral ABCD is an inscribed parallelogram within the circle, then angle A and angle C are right angles, meaning they are 90 degrees. And arc BAD and arc BCD are semicircles, meaning they are 180 degrees, which means segment BD and segment AC are diameters. And if they're both diameters, then they must be congruent. And if the intersection of two diagonals or diameters, segment BD and segment AC, is O, then O must be the center of the circle. And if O is the center of the circle, then segment OA, segment OB, segment OC, and segment OD are all radii of the circle. And if two of the sides of the parallelogram, which must be a rectangle if it's inscribed in a circle, create a right angle, which creates a right triangle with one of the diameters, then the Pythagorean theorem would hold true, and AB squared plus BC squared would equal AC squared. So let's try one more problem. In the diagram, it says quadrilateral MATH is inscribed in the circle. If angle AMH is 11x plus 6, and angle HTA is 9x plus 14, and the measure of angle MAT is 13x. Our starting point has to be with angle AMH being supplementary to angle ATH. Because if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. So I can find x by saying 11x plus 6 plus 9x plus 14 equals 180. That means 20x plus 20 equals 180, or 20x equals 160. So x equals 8. If x equals 8, that means angle AMH is 11 times 8 plus 6, or 88 plus 6, which is 94 degrees. I'm going to skip angle MHT for a minute because we don't really have enough information to answer that just yet. We can find the measure of angle HTA because that's 9 times 8 plus 14, which is 72 plus 14, which is 86. So 86 degrees. And we can also find the measure of MAT, which is 13 times 8. 13 times 8 is 104. So the measure of angle MAT is 104 degrees. Now we have enough information to go back and find the measure of angle MHT, because we know that the measure of angle MAT is 104 degrees. And we know that if a quadrilateral is inscribed within a circle, then opposite angles are supplementary. So angle MHT is supplementary to angle MAT, so we can find that by subtracting 104 from 180, which is 76 degrees. And now we have all the information that we need to find all of the arc measures that it's asking for. To find the measure of arc HTA, we'll follow the endpoints back to the vertex of the angle that intercepts that arc, and we'll see that that angle's vertex is on the circle, which means that the measure of the arc is twice the measure of the angle. So 94 times 2 is equal to 188. So the measure of arc HTA is 188 degrees. Likewise, to find the measure of arc TAM, if we follow the endpoints of that arc back to the angle's vertex, I find out that the angle that intercepts arc TAM is angle THM, which is 76 degrees, multiplied by 2 because the vertex is on the circle, is 152. So the measure of arc TAM is 152 degrees. And again, arc AMH follows back to angle ATH, whose vertex is on the circle. So 86 times 2 is 172, which makes the measure of arc AMH 172 degrees. And finally, if I follow the endpoints of arc MHT back to the vertex at point A, which is also on the circle, then the measure of arc MHT will be 104 times 2, which is 208. So the measure of arc MHT is 208 degrees.